so I'm going to be using VS Code today. As you can see, or maybe you can't see, but that's VS Code. The only extensions I'm using is the C# extension by Microsoft. You can just add that if you don't have it. If you don't have .NET installed, you can go to this link here and you can download that when you need it. And then to double check after install, you just run a .NET version -- version. Oops, not equals. And then we'll see what version we're running. And obviously, as you can see, I'm running 3.1.102. So as soon as if you want to follow along, you can. If you want to just look off my screen and pop out ideas of solutions for these problems, I'm more than happy to keep up with chat and recommendations when we're solving these problems. But I feel like we should get started. So I appreciate everyone coming. For those of you that did come, my name is James Foley. I'm a developer with CodeStack. I have been programming for a little while, a little over 10 years. And programming's always been a lot of fun for me, and tackling math problems or problem solving has been a passion of mine when I was programming, when I was going through school, because a lot of the tasks were mundane, like make a tic-tac-toe board. It's like, okay, I did that. I want something that's actually like hard. I found this site, and so a long time ago, I did a bunch of the problems, and I don't even remember the login anymore. So we're making a new account for CodeStack, and so all you got to do is register. It's free. There's obviously no cost, and so that's my new one that I just started a couple weeks ago. So we'll do CodeStack, and then the credential is, I don't remember. Very simple. 84579. They do this little thing here. Oh, didn't get it right. Dang it, then I didn't even do the code. Okay, I'll get it. Oh, that's why. It's not CodeStack. Hilarious. 58607. Fingers crossed. Yes. All right. So as you log in, you'll have your problems archive, and there's lots of problems, right? So we'll go through one at a time, however many we can do today, and the problems are provided in a way to it's what's called chain learning. So essentially, as you do one problem, you learn processes or functionalities that will move on to that you may use in the next or future problems. So eventually you're going to be reusing these tools and hopefully you develop some sort of a little bit of a library to help you down the road. So we're going to jump right in, and we'll go to multiples of 3 and 5. Obviously I need to set up my project. So just to start off, I'm going to run this .NET new console, because we're just going to run a console app, and it's not going to be any frills here. All right. So we got some files here. We got a hello world. We can just make sure that runs by running .NET run. Hello world. All right, we're ready to roll. So what I'm going to do is I'm going to get rid of this, and let's look at this problem: multiples of 3 and 5. So if we list all the natural numbers below 10, the multiples of 3 and 5, we get 3, 5, 6, and 9, and the sum of these multiples is 23. So find the sum of all multiples of 3 and 5 below 1,000. So multiples, huh? All right. So to find out if something's, let's look at some operators just to just to make note of these things, because we might be using one that is new to some people. So I'll toss in the obvious ones here. Multiplication and division. The one that some people might not recognize is the percent sign, which is division, but this is the remainder only. Oh, if I can type. So this is the division, but without remainder. So if I do 100 divided by 3, it's going to give me, oops, thought I run. I'm used to my little shortcuts. It should give me 33. Now, but if I do the percent, it'll actually give me the remainder instead of the, well, it should have. Oh, I didn't save, my bad. No, the remainder is 1. So obviously it went up to 99 and there's a remainder of 1. So that way it gave me the remainder only. So that'll be useful, I think, when we're doing this problem. So let's look at this here. So we want, they mentioned a sum, right? They find the sum. So we're going to be calculating some sums. So let's do var sum equals 0. And we're going to be incrementing this value somehow. So let's see. Well, I think the best route to start is trying to get this number here. So they give us an example. So below 10, the multiples 3 or 5, they get 23. So let's try and match that result, and then we can try with our logic, try to get this 1000 answer. So we'll go with, does anyone have any understanding of what multiples means? Multiples of 3 or 5? So what that means is, so any number that's evenly divided by that one of those two numbers will be a valid number. So if we look at the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, so below 10, if we try to divide any of these numbers by 3 or 5, we need to make sure we have no remainder. So 3 works here. 4 doesn't work. 5 works because it's 3 or 5. 6 works. And 9 works. So then those are the same numbers that they showed us here, 3, 5, 6, and 9. So it's got to be, they got to go into that number evenly. So let's take that idea and let's go through a loop, and we'll do a for loop. Is there a shortcut? Nope. Come on, give me a shortcut. There we go. Let's see. Let's start at, obviously we'll just start at 3 because 2 and 1 are not very helpful. So we'll do 3 and we'll go to 10 because that's the limit. And we'll do, oh, my bad. We'll start at 3, where x is less than that, and x plus plus. Now, for loop. If you're unfamiliar with the for loop just iterates through this list from 3 to less than 10. So basically, it stops before it gets to 10. So if whatever this test is, if it fails it, it'll get out of the loop. So we'll hop in this loop, and we're trying to find numbers between that we're looking at each number, each loop. We're looking at x to see if it's divisible by 3 or 5. So to do that, we'll use that division remainder operator. So let's see. So if x divided by percent 3 equals 0. We'll add it to the sum. Sum equals sum plus x. Okay, so right now.
Just a question. Can you also have done plus equals just to sum up, like adding?
Yep, absolutely. Could have done sum plus equals x. Yep, this is the same as, yeah, I'll just make a note of that. Sum equals sum plus x. So for those that don't know the shortcut, that's what that means. Thank you. Good little tip there. Nice. It's always
Just
nice
trying to
using less
make things
code.
easier, right?
For sure, for sure. All right, so right now we're looking at where x is 3. We're going to see where x, the number we're looking at, is divisible by 3. We're going to add that number, right? So that'll be 3, 6, and 9. All right, but we don't have 5 yet. So if we do an OR operator, x percent 5 equals 0, we should get the 3's or 5. So let's do a console write line and see what the sum is right now. Make sure I save. All right, sum is 23. Awesome, and that's exactly what we're expecting. So let's go ahead and drop in this 1,000 and see what answer we get. All right, 233, 168. So let's try and drop that in. Oh, look at that. Someone's done this before. 23, 168. Waiting. My internet's a little temperamental, so hopefully, all right. Excellent. So we have a correct answer. They'll give us some facts about, sometimes if you do prime problems, they'll give you some facts on those. And, but looks like this one, difficulty of 5%. So let's go back and see what the next problem is. So that's the first one. All right, so let's hop open the even Fibonacci numbers. Oh, that sounds fun. So one thing I remember doing a lot of is pulling the stuff out into functions. So every time I did a problem, I'd just move it out. I'd just say public void problem 1, and then I just have it in there.
Yeah, I really like that trick. I never even thought about that. Like
So
just taking the problem and making a different equation, but same.
yeah. So say if I want to run problem 1, I just run problem 1 there. So I probably need to do a static. There we go. So that'll still run. So if I go here, yeah, cool. All right, but now we're working on problem 2. So problem 2 says each new term in the Fibonacci sequence is generated by adding the previous 2 terms. By starting with 1 and 2, and the first 10 terms will be 1, 2, 3, 5, 8, 13, 21, 34, blah. Okay, so by considering the terms in the Fibonacci sequence whose values do not exceed 4 million, okay, find the sum of the even valued terms. Interesting. Okay, so Fibonacci is, as it said, you add. Let's see. Let's just do a var x equals 1. Let's call it first, and var second equals 2. So that's our starting point. That's where we have to start. Okay, so the var, no, not version, var. Next will be, by the rules, is first plus second, right? So that's how we eventually have to step. So to get the next one after that, we have to do, does anyone know? If I had to do the next. Any ideas? I'll actually change this to third. I'll change this to fourth. What would the fourth one be? Anyone want to shout out? Come on. Be bold. It's okay to be wrong. Second plus third. All right. So obviously it's going off the previous 2. So this one's going off first and second. The fourth one's going off second and third, and we're going to go on and on and on, right? So we could just do this a bunch of times, but that wouldn't be wise, right? We need the first what, 400, below 4 million. I don't think I want to do this that much. So we have to find a way to appropriately get the Fibonacci numbers. So let's drop these guys. And let's just go back to calling this next, because I think we'll be using that term more. All right, so they gave us a number saying 4 million. So that's where we have to stop. That being said, we have to do this until that next number is, well, that's, while that next number is less than 4 million. I think there's a way to do this. Yeah, there you go. So if you didn't know, you can put underscores they act as commas. So it's, you know, visually you can see what number you're actually typing. Sometimes it's hard to tell what that number is, but with, you know, fake commas, it's a lot easier. Okay, so while next is less than 4 million. So that means while we're generating this next field, we're going to be making sure we don't go past 4 million, because that was the do not exceed 4 million was the limit there. Okay, so to generate these, we want to get the previous two. So I'll need a temporary, I think. So if, well, first we need to check if this number is even, right? Because we have to add the even numbers. Actually, I'm not even going to worry about adding even numbers. First, I'm just going to get some values here. So what we'll do is, let's do it. Var temp equals, so what do we need? For next to be replaced by the new sum of second and next. So really temp is next plus second, right? In this case. But second's not going to change moving forward. So how can we update that correctly? So yeah, there's a problem here. If I run through this.
Sorry, can you explain the underscores first?
Sure.
The
underscores.
I heard you, but I couldn't see it because I minimized my screen and I somehow couldn't pull it back up.
So this is equivalent to, right? So in math, these commas don't actually mean anything, but it's just easier to see. Same for C#. When you put underscores, it's just, they're just like commas. They're not.
All right, that makes sense.
Actually changing the number. They're just the same as commas.
All right, that makes sense.
Cool. So we have to replace next with the next field. So I'm thinking, I feel like first is no longer needed, right? So I don't think we need first anymore. So what if we like just move the numbers? So if we go first now equals second, second equals next, and then next can be the first plus second again. I think that'll work better. First plus second. Does everyone see how that works? Any questions? I think this is correct. And what we can do, what'll be cool is we can just say, let's do 90 here. Well, this is less than that. Let's just console log. I like the CW shortcut. Let's console log next and see what numbers we get for every time next comes up. Actually, let's do it first. So I want to see the first next. All right, so we will .NET run. So we should get a bunch of numbers. All right, cool. All right, so we get 3, 5, 8, 13, 21, 24. So as you can see, these are adding up to the next number. So that's 89. These two add up to 34. That's perfect. Cool. But we're missing 1 and 2. Okay, so we have to keep that in mind because we're starting right at the third step, right? But we'll see how that works later on. So let's see. So it says, all right, so now we're getting the numbers. So that's, if that's correct, we'll put the 4 million back. Should we print out? Yeah, let's print it out. I want to print it out. I don't know if you want to print it out, but I want to see it. Oh, cool. All right, so not that many, surprisingly. I thought it'd be a lot more. I guess it gets up there pretty quick.
That's where those computers take over, man.
Yeah. So I got, maybe I should have done it by hand. No, it's okay. I don't need to. So first, so we got them printing out. Cool. All right, but now we need to, what is it? We need to find the sum of the even valued terms. So what determines something's even? What's a mathematical way of finding if something's even?
Are you talking about even numbers?
Yes.
If it's divided by 2 and equal to 1. And then, well, not equal to 1. Yeah, no.
If
If
it's
it's
divisible
divided
by
by
2.
2, yeah, on an iteration kind of scale.
Yeah. So if it's divisible by 2, so that means if we divide by 2, we should get an answer. We shouldn't get any remainders. So that means the remainder, again, we're using this guy again, 2 should be 0. So if that's the case, let's see. If next mod 2, we'll add to sum, but we don't have a sum. So we need to add a sum. See, this is, once you start, once I start seeing this first and second down here, it's not the first and second anymore. It's some other, 15 steps down the line. It's not the first and second anymore. So this is where it just sort of just, not annoys me, but I just feel like it's more of a clean understanding to have this as a X and Y. Next to make sense because you're stepping, but X and Y is just makes more sense for me because it's not the first and second anymore. But okay, so sum, we'll use that plus equals operand that was mentioned before. And so then we're going to add what next is here. All right. So that'll run through. And then at the end, let's print out, after everything's done, what next. So we're summing up, looks like we're summing up all the even numbers below 4 million, and then we're stepping through. All right, so let's give this a try. See what number we get. Okay, we get 5.7 million. All right, let's give that a try. 5702887. Yeah. Anyone want to? Oh, no questions. That's good. Wrong. Oh no. What do we do? Okay. Why is it wrong? It doesn't even tell us how it's wrong. Okay, so if it's not right, let's print out. I guess a good idea would be to print out what numbers it's adding. So let's print out all the next that it added. Maybe it added, I don't want to say it added the odd numbers, obviously that's not true. Okay, so it added 8, 34, 144. Those seem right. But what's weird is, why is this odd? Shouldn't it be even? I feel like the end number should be an even number.
Maybe you added, or no, actually that doesn't make any sense. I saw the X equal 1 at the start, but then the
Yeah, we
X
don't
equals
add
Y.
that.
Yeah.
Sum plus equals next. Okay, so then let's do system.log or const. Let's do sum. Let's see what the sum is at this point. Okay. Okay. That's interesting. So I think what's happening here is, if I'm not mistaken, I feel like the sum needs to be a long, because it's too it's the number might be too large for might be
So
too
can
large.
what's a long
Oh.
in terms of what you were describing?
So a long, so there's a couple integer types in programming. There's a long, or this is the basic int, right? The traditional int is I believe it's a 16-bit number. Um, or maybe it's a 32-bit. I think it's a 32-bit number. And then a long, so that means it's allotted 32 bits in memory to represent that number. But with 32 bits, you can only make so many numbers because you run out of space. A long is the same as an int, except it's 64 bits. So then you can make really big numbers
Uh, that's some
in memory.
IT. That's some IT stuff I didn't know.
Yeah.
Even in IT, that's what matters.
So that's where memory, where the memory comes in, where you actually care about what value you're using. If you're really using with big numbers, sometimes it matters. But okay, so here we go. So uh, let's do sum plus next. I'm curious because it says the sum is this on the last sum. But then it gives me this. So what am I printing here? Oh, that's what no one noticed. No one told me. I put in the next digit instead of sum. All right, so that makes more sense. Okay, so the last sum is 4613730. All right, let's try that. 4613730. 4613730. Still wrong. Okay. Any ideas? What numbers are we adding? 8 4. I know. I see it already. I see it. The first number. Since we have 2 up here, we're not actually adding 2 to the list. So we should just start with 2. I think if we start with 2, 3, 5, 8. Yep. Because two. I think 2 is the number we're missing. So
Yeah. You're right.
2 is the number we're missing. So let's get rid of all the extra prints. I don't need that. I still printed a bunch. No, I know I'm running it for no reason, but all right, cool. So let's try that. Oh, sounds promising. Oh, yes. Excellent. All right, so that's 2 problems down. So again, we revisited this modular number, this modular symbol to emphasize the divisibility of even numbers. So let's go ahead and go to the third problem here. Is any questions so far of anything we've touched on, programming or math related? Any questions? Fine.
Imagine if you didn't use the plus equals.
Oh no, there'd be like at least 6 extra characters I would have to be typing. All right, so we got 2 down. So let's drop this out. And let's put this into public static void problem 2. All right, so let's work on problem 3. Right along. Largest prime file. Primes are terrible. All right, prime factors of 131, 95, or 5, 7, 13, and 29. What is the largest prime factor of the number, whatever that number is? Okay, that sounds intense. Okay, so prime factors. Does anyone know what prime factors are by chance? It's kind of a new topic here. So we
It a
go ahead.
number that's non is not divisible by any other number besides the number that it was described as, kind of in a sense.
Yeah. So a prime is a number that's only divisible by itself in one. So 3, 7, 11, these are all prime numbers because they can't be split up into another multiple. Now, prime factor, so we touched on factors before. A factor of 3, 5, a factor of 2 makes something even. So that means it's divisible by this prime number. And so we have to find this prime factor of this giant number we're looking at. So I'm just going to put this number here. It's always going to be a long var long number 60. This is where I copy paste. I'm bound to typo if I try and type that out. All right. So as you can see, this is a long number. Now it's a long number. Great. All right, so that's our starting point. So primes are tricky. There's no real easy way to just grab primes. You can't just like skip 3 numbers and find the next prime. It's really you gotta sort of build a library as you go to get primes. So we're gonna have to start with a list. So we'll start with the primes list. And I'll just make this a basic list of longs since we're working with longs. Oh, it looks like we have our first library to use. So we'll use link. Sometimes I forget which IDE I'm in. So using system collections generic allows us to use libraries like list arrays, essentially. So we'll be using that for our primes. And then we'll have to keep track of the factors. So all these numbers that are going into these numbers. So I'll just do the same thing for now. Factors equals new list. Okay. Let's see. So obviously we might as well start.
I kind of have a question off track kind of thing.
Sure. Go ahead.
So you were saying that you were using the systems collection generic, but what was the previous system settings that you were using? Is it more like
Oh,
a set of rules that describe what you were using offhand kind
uh,
of thing?
the one that was there before was system, just system, using system, but I wasn't actually using it. It was just there. As you can see, it's grayed out.
Okay. So it just increases the rules in terms of like what's been pre-built.
Right. So this just tells you which libraries are being pulled into this file in this class of what's actually required to run. So if I get rid of this, when this is compiling, it's saying I have no idea what this is. Like this is not normal.
Yeah.
This is not normal stuff. So that's why you sort of have to tell it where to find this list object.
All right. So the part that I was kind of confused on was that you can get rid of the pre. I can't even think of the word.
This one, this previous one.
Yeah, the previous one because the new one encapsulates those new rules as well.
No, not exactly. So if I was using something in system, sometimes it's so
Okay, so you
if I
kind of
did
might want to stack those rules just in case, kind of thing.
say for example I got rid of the system dot. If I got rid of the system dot and just did console write line like normal people, it would require me to keep it. So if I got rid of this, it would say I don't know what console is because that's
Yeah,
part of the system library. But since whenever I do CW tab, it just does the system dot for me. I don't actually need to import the system library. because it's automatically linked by the system dot. But if I don't want to do this, and on top of it, if I want to do, say, for example, I could also do this, where I got rid of, and I can do system.console. I think I can do this. Does that let me? No, it's an object. It's not a library. Okay, that doesn't work. But that being said, this still. Yeah, so this, because this is in the system library, it knows where or how to call it. But since I was using system dot ahead of it, it doesn't, I don't necessarily need this. And you'll see that this is an unnecessary using directive. So that's why I went ahead and dropped it. That makes sense? Hope so.
Yeah, it makes sense. Thank you.
Cool. All right, so back to this. I think I wanted factors. I think I accidentally deleted it. Okay, so I have primes and I have factors. How do I get these factors? Well, I have to iterate through the numbers. I think a smart thing to do would be our test number equals 13195. That's the number they gave us. See why copy paste is handy. All right, so 13195, that's our example number. And we should get 29 as an answer. So our hoping for, let's spell hoping right, 29. Okay, so we got our test case, and let's see if we can make this happen. Okay, so obviously we're going through a loop because we got to go through all these numbers anyway. So while, I think I need for I equals 1, while I is less than test number. Let's see. While I is less than test number, if it's divisible by this number, that means it's a factor. Well, I don't want 1 to be in there. Let's start at 2, because obviously 1's going to work every time. So that's not a number we want. So let's start at 2 and say primes, or sorry, factor, if this test number is divisible by whatever I is, then it should go into the factors list at I. Okay. Okay, so we will increment, I guess, I, and to move on. What will that do? That will give us every number that's a factor in that. So that's fine. So for each, does it give me a nice for each statement? Great. And factors, let's just print out those numbers. Or I just want to see what happens. So here's what I'm doing. So I'm finding if the number list we go through is divisible, evenly divisible into the test number, I add it to the factors library. And then once that list is done, I am printing out the factors list. So I just want to see what that list looks like. All right, that's fine. I just want to see what's going on. Okay, so we got 5, 7, 13. So these are all the numbers that are divisible into 13, 19, 5. So let's see, this is where the underscores are helpful. 13,195. I want to see what this number is. Probably not even a number I know what I say. 600 billion, 850. Yeah, that's a big number. Okay, so all the factors that go into 13,195 are there. So what are we actually looking for? So we have all the factors, but it's not the prime factors. So we need to figure out whether or not these numbers are prime. So it looks like they're all odd, so that's good. Some of these are end in 5, and obviously those are not divisible by. End in 9 might not be divisible by. But let's see. Got to figure out a way to store primes. Let's see. How can we do this? If anyone has any ideas, please, feel free to speak up.
Use an if statement. If it is divisible by the prime numbers, store it.
Okay, so if it's divisible by a prime number, but that's what we're trying to figure out. Like, we don't know the primes. So this primes array is empty right now.
You're right. I'm thinking a step ahead.
Yeah. So we got to get these primes first. So let's step through these factors. All right. So we'll again go through these factors. So this is call this F. And I want to step through these and find out if they're divisible by anything larger, I guess.
So I guess we got to use an if statement for that one then, right?
Yeah, I really want to use link here to try and find some stuff, and I think that'll be a little too confusing. So I'm gonna try and use a different route. So let's say
links if that's what you're trying to go.
No, link is just it's a library that for those that don't know, it's a library that lets us do functions on an array to try and get some useful information. But I really want to step through this as basic as possible.
Yeah. That makes sense. All right.
So let's see. Factors. So when we saw our prime, these aren't primes. All right. So as I go through this list, how do I know what's a prime? Well, in primes, I know a couple primes.
If it's divisible by 1, 3, and 5, in a sense, those are the first 3 numbers I can think of.
Yeah. So let's start with a initializer. 2 is prime. 3 is prime. So let's start with that. Okay. So if it's divisible by any of those numbers, well, let's not add 1. I don't like adding 1. It's too easy. So if it's divisible by 2 or 3, it's not prime, right? Because then it's not 1. But if it's not divisible by 3, then we can go ahead and add it to the list. So let's try that. So what we'll do is for every factor, if this will be an inner for loop. Ooh, this is gonna be dirty. Int prime. Let's call it pry. And that's and pry is no, we're gonna do index I. Sorry. Well, I is less than primes. Yes. Dot length. Size. Count. What is the dang? Count. Yes. Sorry. So many libraries you start forgetting which. All right. So here I'm iterating through each. What's the problem here? Oh, there we go. Oh, it doesn't like it. I might finally have to use link. Yep, there it is. All right. Why don't you like this? Cannot be. I already used I. Okay, fine. J. Okay, so here I'm iterating for every factor. I have to iterate through these primes over it. I have to start over basically. and say if j, oh, sorry, primes at j equals 0. All right, so what I'm doing here is, so this is, I'm indexing this primes as an array. So primes, let me use some notes here. Primes, so say we're starting at 0. This is going to equal 2. Because we added that to the list, right? Because it's right here. Then as we go higher, primes 1 is the next number, whatever it is. And right now we only have 1 and 2, or 2 and 3 in there, so it'll stop after that. So if this is true, so var it, not break, var is prime, false. I'm just going to say it's true, because if it gets into here, that's going to break it. So is prime is false. So what's happening here? So I have this is prime flag, and I'm going to hop into this array that's going to go through each prime and say, is my number divided by this prime? If it is, then prime is true, or prime is now false, because it's this f that we're looking at is not prime. All right, so if is prime, and we will add it to the primes list, primes.add. Oops. Primes.addf. Okay. Does that make sense? Any questions? A lot just happened. No questions. All right. I'm hoping I'm not losing you guys, because I want you guys to be able to keep up and see what's going on. My phone thinks I'm talking to it. So let's see. So we have this list of potential primes now, right? So let's just may as well see what that is. So now for each for Pn primes, P. Let's see what we get there. Oh, we almost messed up. Oops. We want this to be in the for loop. Or do we? No, we don't. Just kidding. We want it to be in the outside loop. That's right. Okay. Yes. Good. Good. All right. So let's see. Let's see what happens. Best thing to do is just run it. As long as it compiles, we got progress. All right. So we got primes. Are these prime? 2, 3, 5, 7, 13, 29, 35, 65. 65 isn't prime. I don't think. No, it's not. Okay. Well, we got a good start up until 29. Then we lose it. So what happens? Let's see. If f is divisible by this, I think the problem is that we're going through each of these numbers of factors, because we're just looking at those numbers by themselves. We're not actually looking at all the primes. So I think we have to go through and find all the primes in the entire list. So if we do the prime search up here, where we're actually doing one from I to the test number, we might be able to find more primes and more efficiently solve this. Does everyone see that? How 35 is obviously not prime, 65. Not sure how it's getting these numbers, but I feel like it's using the factors, because those are the only numbers we're going off of from I and from 0 to the count to the size of the list. So 2, 3, 5, 7. See, 11's not in here. Neither is 17. So we're definitely not getting all the primes. So I think we need to make sure we get primes. Okay. So instead of going through the factors, let's go through the actual big list of numbers. So we'll run sort of the same concept here. Do var is prime equals true. And then for int j, I feel like copy paste is more efficient here. Okay. But this time it's not f we're looking at, it's I. And then we're looking at each one of these is 0, right? And if it is prime, okay, if it's prime, we add it to the primes list. All right. So hopefully that gives us a better, so let's get rid of this. So this factors thing isn't quite working out yet. We'll get to that. But we're going to print out the primes again and see if we get something better. And just to make it go faster, we're just going to make this 195, just so we can get a little speedier result. Okay, see, that's way off. So now we're printing all the numbers. 2, 3, 2, 3, 4. Okay, that's odd. So I started it, oh, because I already have these, obviously. All right, so I don't need to do that. Okay, 4 shouldn't be in there. All right, so I'm going to introduce debugging because that's going to be important here, I think. So I want to try and debug this because this is not getting very friendly. So let's see. Let me open up my start debugging. Oh, I need a debug statement. Let's start before we do the loop. So I marked this little break here, and it'll let me stop. Oh. Core, yes, yes, do things. I don't need that. Try that again. It made some files for me to make it so I can compile. So it should. Boom. All right, cool. Debugging. And we can look at stuff while it's happening. What time is it? 7:04. Got plenty of time. So we're looking at this, and we can see I. We see primes is empty. The test number is 195. Okay, so that's fine. Test number is divisible by I. So what was test number? We're not even looking at that right now. We're just looking. We want this part. So I'm going to add a breakpoint here. I'm going to ignore that guy. Okay, so again, still empty. I is equal to 0. Okay, so it was empty, so is prime true. And right now we're looking at I, and that's, what's I? I is 2. So yeah, that's right. I plus plus, sure. All right, so it's going to go ahead and do that stuff. So now I is 3. Primes is a little bit bigger now. That's good. Okay, that ended up working out for that. Primes.count. Okay, so 3 is correct. So I is j, so is prime. So I feel like it's not even going in here. Oh, huh. I feel like I is 4, primes count is 2. How is I? Oh, that's the problem. See? J. J is what we're looking at. And I is just supposed to stay there. We're supposed to be looking at J, the index. So that's why everything's suddenly true. All right. Dang bugs. All right. Let's restart this thing. Terminal. Okay. Obviously that didn't do what I wanted. Did I save? I don't know. Oh, I didn't save. That's right. Okay. Let's see. See if that made a difference. A little bit. All right. So now we didn't get 4. So that's good. 5, 7, 11, 13, 17, 19, 23. These are all looking like primes to me. Cool. All right. We're in a good spot here. All right. We're good. We got ourselves some primes. All right. So we got primes that are in this 194. 195. So if I put this number back, 131 or 13. All right. So I'll get a list of primes and I should get a list of factors. So let's print both. Let's go ahead and just have a little comparison. F. Let's see here. So we're going to get lots of numbers here. This will be exciting. All right, lots of primes. Lots and lots of primes. Look at all those primes. Hot dog. Dang, I didn't even get to see them all. Okay. Well, that's not friendly. So let's not do that. Let's make sure we're still getting factors. Okay, it looks like we're still getting factors, so that's good. Okay, so then what we have to do is then we have to find out of these, what is the biggest number that's in our primes list, right? So we'll just go from the bottom, from the end to the, until we find one that's in there. So F in factors, I don't want to do it this way because this will be slightly slower. So var F equals factors dot count. And then we'll stop at, so while F is greater than 0, F minus. Oh, goodness. Goodness, something's not happy. Why is there so many Fs? Factors dot count. That should work. Yes. Why are you not? Oh, duh. 4. Wrong for loop. All right. No, it doesn't need that. Let's get rid of this. And this is what it doesn't like. This really. It doesn't like minus. Why not? Why don't you like minus? Oh, that's why. Plus F is greater than 0. All right. See what happens when you try and outsmart the for loop. Okay, so if this is true, greater than or equal to 0. No, greater than 0. Let's just do that one. All right, so we're starting at the end, right? So we're have to do it the correct index. So this will be -1 because that'll be bigger and that'll be accurate. Okay, great. So F. So we're looking at the factors. Factors at F. We want to know if it's in the prime list, right? So that's the target. This is the one we're looking at. Let's see. So we have to loop through the primes list, we'll call that PR, if PRs equal to factors F, then, I mean, we only want the first number. Let's just console. Let's just CW this PR, and then let's just return. Just get out of the whole thing. I mean, some might do a break here, but this break might only break this loop. But we still have the outer loop, so that's why for loops, like going into multiple for loops is kind of cumbersome. So we'll just return. We'll have a print statement. So let's see what this spews at us. Hopefully nothing too crazy. 29. That was pretty easy. And 29 is in the list. So it says all the rest of these are not prime. So that's interesting. Okay, so let's see. Largest prime factor, is it 29?
It may be the fact that you're looking through the numbers and you're not dividing by prime numbers as well. Because I mean,
but we have a list of primes, and we have all the factors.
But are you dividing by even numbers as well? Because even numbers do define what a prime number is.
Well, even numbers are not prime, so that's why there's no even numbers in this list.
True, but I mean, 15 is a prime, or isn't a prime number, but there's a odd number there. No, wait. No, I got that confused. I was thinking about the whole, if you define odd numbers by odd numbers. I'm confusing myself. These prime odd numbers make me very confused. That's why these puzzles make a whole lot of sense.
All right, so let's go back here. This. All right. Okay, so I see why that's the 29 is not the answer we're looking for, but it is the largest. It's because we have these guys, this example here to show us that our logic is actually correct. So you're seeing these numbers here. So let's actually talk about what's actually being printed here. So let's actually just clear this. And let's first print our primes. Actually, do we want to print our primes? That was a lot of primes we showed. Let's do, I think in this case, it'll be fine, maybe. Let's print out, I'm having a hard time thinking here. Let's print out the factors. So these are all the things that are in this number that are divisible in this number. So if we just do this, let's go ahead and not worry about this right now. And let's run this. So right here, we're looking at factors of this number, of this test number. So we'll say CW factors of test number. Okay, just gonna do it one more time. So we have a nice understanding here. So the factors of this number, so all the numbers that can go into this number are 5, 7, 13, continue all the way down this list. So if we divide 130, 195 by any of these numbers, we're gonna get a solid answer. We're not gonna get any decimals. Does that make sense?
Yeah.
Yes. Cool.
Yeah.
All right, but these numbers aren't prime. Like they're not all prime, right? So these are just the factors, not the prime factors. The prime factors are the numbers in this list that are also prime. And so that's why when we made a prime list up here, we made a big old list of all the prime numbers that are below this number. Oops, below this number. Like there's no way, we didn't even need that many numbers. We just needed like that much. That's like not even half. But nonetheless, we did it. So that being said, we have this giant list of primes. Then we went through for each of our numbers, we print out the very first number starting from the bottom. We go through here. Actually, what we can do is if PR is not equal, oh, I'll just do an else statement. That'd be smart. Else not prime. And we'll just print out the number so we can see what's actually happening. Or no, you want that one. Factors F. Okay. For each of these, do this. So if it gets out of this loop, it's not prime. So what this is saying is, for every F factor, and I go through this, if the app is still running, then that number is not prime. So that's why I say not prime. And when the app stops, it will be prime. So this one is all right. So let's see this. All right, so we got the factors here, right? We have our factors that goes to here, and it goes through starting at the bottom because we're looking for the largest number, so it's the most logical direction to go. We see all these is not prime, not prime. And then finally, prime is found, 29. And if you look at this list, the largest one is 29. So let's go ahead, being that this logic seems to be working, let's go ahead and try this big number. So we're going to do number instead of test number. And do that there. Now my concern is generating these primes might go crazy because it's a huge number. Kind of curious how that's going to work out. Because I'm going to make a big old array of primes, you know, when that goes through.
But, we're going to hook up a lot of PS3s and make them a calculator.
Man, no, I don't think it'll be that bad, but we'll see right now. Largest prime, and we're going to go through a lot of not primes here too, because it's going to start at the very last. I don't even think I want to print this out. So let's not even print this out. All right, so let's do it and see what happens. It's doing stuff. It's doing stuff. Don't break. Don't run out of memory. What number will you give me?
PS3. No, I'm just kidding.
Yeah, it just returns the letters PS and 3. That'll be great. Let's see. Now remember, the big problem here is that prime library that we've created is huge. So it's going through each of those to try and find the correct number. Now the primes do get more spaced out as we go up in numbers, but be curious to see how long this takes. What time is it? 7:20. So we got plenty of time. Might even be able to do one more problem if this even runs. Now this is where optimization can really obviously help. I do know a couple ways where we can make this faster, but let's just see how long this takes, and hopefully it doesn't fry my computer doing simple comparisons. Oh man!
You want to run us through the whole logic from beginning to end, just depending on how long this whole thing takes.
I mean, sure. I don't mind. So again, we're looking at looking for prime numbers, the largest prime factor for this problem. And the way we're doing that is first this number that we're targeting is going to be our limit. That's the highest number we can go to. If this number we're looking at is divisible by any number going up to that number, we're going to add that to the list. Oh, you know what would make this a lot faster? Is if we stop at the biggest factor instead of all the numbers. That would make our primes list a lot smaller. This is still going. So anyways, so we're going through and we're looking for all the factors. All right, so we add that to the factors list. Sorry, all right, these are all the numbers that are nicely divisible into our target number. While we're doing that, we're also making this prime list, and that's this part right here. And this prime list, we're trying to figure out all the primes that are below this number, and we do that by looking at that number and seeing if it's divisible by anything in the primes list. So right when it starts, the prime list is empty, and the first number we start with is 2. So the first number that goes into this list is 2, and then it goes on and says, well, 3 is not divisible by 2, so it'll add 3. And then it'll go to 4 and say 4 is divisible by 2, so this is not a prime, so it won't add it to the list. And it'll go to 5, and 5 won't be divisible by 2 or 3, so it'll be added to the list. And it'll continue on with this logic, and adding it to the list and making this giant primes library for us. Unfortunately, this program will run too long for us, so we're gonna do a quick adjustment. A little Control-C stops the program for us. And what I'm gonna do is, instead of doing this while I'm in this loop, I'm just gonna do a separate one. We'll do a while Q, stop it. While Q is less than factors. I'm gonna get the biggest number in factors. So that'll be factors count -1. So that's the biggest number in factors, and that's where I'll stop. I don't want any numbers bigger than that because that won't make sense. Okay. All right, so again, I'll do this, and then instead of I, I'm going to be looking at Q now. Let's change that to Q. Get that one. And I'll change this to Q. Okay, so we have 2 loops now instead of just using this. Instead of sharing the loop, I separate its own loop and really minimize the amount of primes I'm finding. So what we'll do is we'll run this and see if this helps speed up a little bit. No guarantee, but it's a start.
Okay, so what you did was you separated it into 2 different equations running at the same time versus just running one equation that has that other equation included.
Yeah. So I made it into 2. It's still doing a double for loop, which is really costly, but I'm hoping this at least makes it slightly faster.
Yeah, nah, I kind of believe it does, just because it's going to run simultaneously versus running over or inside that other one.
Well, running it inside actually makes creating the arrays efficient. It's fast, but it's the fact that later on, okay, unhandled divide by 0. Oh no, somehow there was a 0. Where? Line 16, right here. Somewhere I is 0. Interesting. Oh, maybe this needs to be a long, because maybe it gets too big. That's possible. Let's just make everything longs. So what happens is that this factors. So say in the 131.95 example. I wonder if I have the numbers. So in this example, the largest factor was 2639. So that's the biggest number that could even be in this list, right? But our primes were up to 12,000, some. But we don't need those primes because those aren't even in this factors list. Like it makes no sense to have them bigger than that number. But let's see if this can.
So, are you saying that we needed a if true statement kind of thing?
So basically, what I'm trying to say is, if we have this list of 1, 3, we just have this long list till 13, 600, 501, whatever. Pretend that's a prime. We have this big list of, so every time we want to compare these numbers, we have to go through each of these numbers to see, is this one prime? No. Is this one prime? No. Is this one prime? So it's a really big number. It's a big problem for us because we don't want to go through all those numbers. So the way I'm hoping to limit it is that I'm only looking at the biggest number possible in the factors. So the biggest number possible was 200 and something. So then I don't want any primes bigger than 200 and something, is what I'm getting at. And so the primes list will be a little bit smaller. Just hoping we don't get any divide by 0 again. Come on. Come on. Don't break.
Black holes created.
Yeah, it's working really hard. I can hear my fan.
I definitely. Oh no, I don't. Yeah, I don't agree with fans sounding like that.
All right, so let's look some more and see if there's any additional ways I can improve this logic here. So obviously the double while for is very taxing. So maybe I can find another way to do this. Let's see.
I think instead of a while, you should probably use an if statement in terms of like, if that thing is true, then maybe it'll work, or it'll maybe turn out that number that you want to take out real quick.
Well, I am using an if statement. The problem is we have to check every prime. We don't know which primes are in it and which primes aren't. So that's why that's why these problems, like you can't do these by hand. This take too long to figure out. But sometimes, depending on how you program it, it's taking forever just to wait for the computer to figure it out. Obviously, there has to be a way for us to improve this logic, and there is. I know a couple ways. I'm just trying to see what would be efficient in terms of getting these to come out right. So generating the primes, I don't think we'll get much. I don't think that's where the main problem lies. I think. One thing we can do is see, we haven't even gotten this guy. Right, so I think we're stuck in this area. So while Q is less than factors, let's do CW. Let's see what factors is. Okay. So we're just gonna pause the rest of this. Let's see. It's too slow for us. We can do better. So let's see what the largest factor was. If it wants to. Yeah, I know. It's complaining that this number is never used and this number is never used. Or this number is used. Why is this complaining? This number is assigned, but its value is never used. It's used right here, bro. I ignore you. That's interesting. There's no reason why this should be breaking necessarily here. Okay, that's fine. We can let's debug then. Well, I is less than number, and number is some giant thing. I plus plus. Let's see. All right, that's huge number. Good. So as you can see, I is iterating from 1 to this huge number. So it's a big step every time. And to have to do this entire thing until we get to here is a process. So what's the first factor we add? So we added 71, 839, 14, 71. Some big factors there. Okay, that was it. No, not just kidding. I'm gonna put a breakpoint here, and let's see. See if we can get out of this. It's interesting.
Fingers crossed. Fingers crossed.
It's interesting because I don't imagine this being a big issue as far as okay. So here, I is what? This is I is 4. This is
46
million, billion,
35.
4.6 billion.
Yeah.
And we're at 4.6 billion, and we need
God.
a lot more. Holy smokes! All right, come on, computer, don't fail me now.
I mean, it feels like it's closer than what your RAM was going through last time.
I just wanted to get to here, so I just want to see the biggest number. You know what we could do is instead of adding by 1, what if we add by 2? Because if we add by 2 on an odd number, then we don't have to have even numbers in the list at all.
Yeah, you can skip 1.
Because like 4, 6, 8, even if it's divisible by that, even if it's in the factors list, it's not a prime. So we don't even need it. So let's do this. If I equals 2, actually, let's do I equals we'll do I plus 1, else I plus 2.
What did the question marks mean?
All right, so what this means, so little, if I equals 2, I equals I plus 1, else I equals I plus 2. These are equivalent. These two, this logic here and this logic are logically the same. But as you can see, obviously the top one is much cleaner. So basically what you're saying is, if this is true, do whatever's after the question mark. If it's not true, then do whatever's after the colon. And as you can see, we have sort of the same thing here. If this is true, do the I plus 1. If it's not true, do the I plus 2. That makes sense?
Oh, okay. So it is an if-else loop in a sense,
Yeah,
but just
it's
shorter.
basically, yeah. It's an inline if-else statement. So
yeah, that makes a lot of sense. Thank you.
Okay, so let's go ahead and comment this out just so we can get this rolling. And let's try this one. Let's see if we can get something faster. Just a little bit faster. Twice as fast would be a lot of help. Because if it's incrementing by 2.
Yeah, the only way I've ever used the question mark was for that else check. It was never for if
I see.
else. You know,
I
you
see.
know what I mean? No, I actually had the reverse, but you know what I mean.
Yep. So let's see if we can get the largest factor. Oh, sometimes these things can take a while. Hope I'm not running anything in the background. I think I'm running like a whole server because I was working earlier. No, we should get an answer. I want to at least get this one done before our time's up. But sometimes programs can only think so much. Yeah, there's no way we can increment anymore because if we increment by 4, no, because you might skip an odd number. Damn. Oh, it's so sad to see this struggle. It's just a while loop.
Honestly, though, it's a third world or first world problem kind of thing.
All right, let's see. I wonder. Oh, I should have debugged. That would have been smart. Then I could actually pause it and see what its progress is. Hmm. See, where is... I'm trying to be patient here. Out of curiosity, while we're waiting for this awesome logic to run, um, anyone finding this interesting as far as looking at programming as tackling puzzles instead of just build a website, make an API that gives you data? Um, what's your thoughts on the site and the problem so far? You can message in chat if you want to, or if you want to, shout out in voice, that'd be great too.
Honestly, I like this whole puzzle aspect more than I like building websites, and that's just from me saying I have built websites. They're not hard to build. It's just a lot of problem solving as well. But this is more problem solving in a sense. That's just my
Yeah,
opinion, though.
for sure. Okay, so Steve has a question. It says, this is very interesting perspective. How often do these kinds of problems come up as a developer? What's interesting is that the types of problems where you're going through loops or going through large amount of data comes up a lot if you're dealing with the API and you're dealing with a large quantity of data. And that's why we sort of we leverage databases to give us to query information. So that's why databases just handle data so much faster than our CPUs can handle them by themselves, just like line by line, basically. And because of that, that's why we use that utility to query data and get that information. Lots of times when you're doing some of these puzzles and you're dealing with lists and bulk data, how you cycle through that data can have a big factor on your performance overall. So I've noticed when you start tackling math problems and you see problems like this, where this problem is actually taking a while just to iterate through 600 billion numbers. I mean, imagine like Facebook having to iterate through 600 billion users to do a search, right? There has to be a smarter way of doing this. So obviously they have smart ways of doing it, and we're just doing it the most rudimentary way possible, just iterating through one at a time, saying, hey, are you it? Hey, are you it? So that's where utilizing resources really plays a big factor in how your app performs. Hope that answers your question. Now, dealing with prime numbers and factors, does that necessarily come up? Not so much. Lots of times it's pretty common to deal with even numbers, just because sometimes paging or certain aspects of finding pages. So say, for example, you have 10 pages of however much data, you do a modular 10, you know which section of page you're supposed to be on, and there's mathematical ways to calculate those numbers to make it easy. Thanks, Omar. Omar said, I enjoy having all types of variations in teaching learnings when attending CodeStack meetups. Yeah, I appreciate that. We're really trying, I really wanted to make this sort of a completely different aspect of programming, because everyone, I mean, the obvious route is you want to obviously want to work, you want to learn what's important for the job, but you have to understand that programming started way before just trying to build websites. We wanted to solve math problems faster than we could do them ourselves. So that's really where this comes in. Now, unfortunately, this is still running super slow. Oh, it's breaking my heart.
Hey, James, if I could just jump in for a sec.
Sure.
We're looking at Project Euler right now, but I know that I've used a similar site, Code Wars. There's lots of different sites that are available that run you through problems like this, or trying to find solutions to small problems, and they get exponentially more difficult as you kind of become more practiced.
Right.
So for the folks that are attending or watching, there's lots of websites that are free to utilize if you want to brush up on your skills, and it's a nice way to sort of kind of sharpen your tools a little bit, to get in like the math problems that you've been doing tonight. These are definitely practical. I could see something like this being utilized in some of the applications that we're developing in-house, where we're moving just tons and tons of data, and trying to pick it out, or building algorithms and things of that nature. But there's lots and lots of resources available, Code Wars being one, Project Euler being another. There was another one that we used to play with just for fun, but they're out there, and they're for all different kinds of programming languages. So if you want to stick with something, stay with JavaScript, or move into C# or Python, or any of those types of things, all of those are available out there to kind of, like I said, build your toolbox a little bit, and expand your knowledge, and get some practice in. And if you're looking for employment, it's very common to run into a situation where they give you whiteboard problems to solve, and that's very similar to this as well, where they'll give you a problem to solve and you have to write it out longhand. So any practice you can get doing those sort of problems, and kind of shake out the butterflies, so you don't get nervous when you see a problem like this written out and then having to code it, is incredibly helpful.
Yeah, that brings up a keen memory I have of when I was doing an interview. They gave me a giant file. They said, they obviously didn't give it to me, but they said, you have this library of, 1 million numbers, and we want all the unique numbers. Like, go ahead and just give me the logic. You'll get an array of numbers, and just show me the logic you would do to give me all just the unique numbers, because there's duplicates in there. I just want the unique ones. And so
I have a question regarding that.
Sure.
Do they usually allow you to use a computer to do that equation, or do you have to build it off of just logic wise on the whiteboard?
Every time I have done it in person, it's always been on a whiteboard. You literally write the code. Like they say don't worry about syntax, like semicolons, like that's this trivial stuff. Get the logic, right? Get the logic that you want to sort of put out, and think you want to talk out loud when you're thinking. Like I did my best to do that here. Sometimes I just think internally and then sort of talk about what I was thinking. But when you're doing stuff on whiteboards for interviews, it's definitely important to sort of talk about what you're thinking and why you're doing this logic. And then as you're talking, you'll even catch yourself like, no, that doesn't make sense. And then I guarantee you they'd appreciate that. I'd appreciate that if I was interviewing you, because you're taking the effort to really understand the problem, and when you understand the problem, you can tackle it more efficiently. So yeah, when I did this on the whiteboard, it ended up working out fine. But I didn't get that job. But that's another story. But I have done other interviews where it's remote, where they send me a link and they say there's 4 problems on this site. Just go ahead and write the code in any language you're comfortable in. And at the time I was most comfortable in Java, so I did it in Java. And so then I submitted my code, and they would run it and take a look and go from there. So that's sort of the 2 ways of getting sort of whiteboarded.
Oh, wow. So when you submit applications online, they just ask you to try to build your own equation and then submit it to them in a sense?
Yeah, so they would give you a box to dump in your code. Like they just like paste in your code. So you just take this, copy paste into there, and then they would look at it, try and run it. If it doesn't run, they're just trying to understand your logic. You'll definitely want to try and add comments if you're doing that. You want to say, this is why I'm sort of thinking this, add comments to this. And that also gives you a good anecdote for them, because they see you're commenting your code, you're understanding that someone else has to look at this code, and they don't have to try and figure out what you were thinking. So that's very helpful when you're trying to just ad hoc sort of a problem, on a board.
Okay. Yeah, I understand what you're saying. That makes a whole lot of sense in terms of those interviews, especially the new route that we're taking and everything. So yeah, I appreciate that insight. It really does help.
For sure. Is there any other questions? Feel free to send them over to chat if you would like. Man, I was really hoping this dang loop would finish. I'm gonna stay until this loop is done. I'm gonna check my answer, and on the video, it'll be there. I'll even have them cut it. Like, even if I have to wait an extra half an hour, I'm gonna get this answer. But I'm gonna wait. It has to show up. It has to work. It doesn't make sense to not work. So incrementing by 2, it's just such a big number. It's so mean to make us use it such a huge number. I almost feel like I should have found a prime. I should have found something that was divisible by, and then just stop at that number. Can't do that now, but it's okay. Let's say 6008 514.
The problem that I found when I was coding for the most part was that while loops are really hard to use, especially when you're using like if statements inside of them. It makes sense, like it honestly does, but sometimes when you're iterating through so many numbers, it doesn't stop. So
Yeah,
with
sometimes
just regular
much.
if loops, even then it can still do the same thing. But man, it does kind of help to just break down those iterations at some point.
Oh, this is killing me. All right, I stopped it. I'm gonna do this another way. It'll be much faster, I think. But first, I have to debug. What I'm gonna do is I'm gonna grab the first number I see here. It's kind of cheating, but it's not. I'm gonna say it's not cheating, but I want the first factor. The first factor is 71. So this number divided by 71 is 8 million. Oh, that's a much smaller number to deal with. Let's do that. So I don't even get here. That's what's frustrating. Let's do. So what I did is I did this number divided by the first divisibility I found, which was 71, and that number is 8462696833833. All right, so that's that number. And just because I know how math kind of works, I know that nothing bigger than this number is going to be in the list. So I can make this number be here. Because I know 7 is going to be in there. This number will be in there. Actually, let's do +1 just to make. All right, so I'll stop this. See what happens. 8 million. There's 8 billion. Yeah, thousands, millions. No, it's 8 billion. Should be a little bit faster than 600 billion. I'm hoping.
While we're waiting for that to run, just so everybody knows, we do these meetups twice a month on every other Thursday. They start at 6 o'clock. They usually run till about 8 o'clock unless we have some folks that have some questions and it kind of pushes a little bit longer. But if, excuse me, if you have, if you've missed one or you want to check on some of the ones we've done in the past, we do have a YouTube channel. Hey, congratulations. Look at that.
The largest factor is that.
Yeah.
Nice.
So
Good job.
now
we do have a YouTube channel where we post the videos from these meetups after the fact. Usually takes a week or two to get them edited and posted. I'm going to post a link to that YouTube channel in the chat box if you guys want to take a look at that at some point. There you go. Feel free to look at those and put on your schedule to be here in 2 weeks when we'll have another one. Subject to be determined.
this should work. This should be just as slow as the other one, just as fast, because the second lists are much easier to go through. We shall see. The excitement. I'm excited. I can't wait to see this answer. This is where you check Twitter and do other things to busy your brain. Most of the time when I'm watching stuff build and I'm waiting, that's where I go back and sort of make comments, delete stuff that I don't need anymore. You know, to use your space time to clean stuff up.
Good question. In terms of like the mathematics portion of it, do you ever use like that one website? I forgot what it was called, like Wolf. I can't remember what the website was called. It's been so long since I used it.
What is it?
It was like Wolf something. It was like Wolfram or like Wolfram Alpha. Is that one? Wolfram Alpha. That was just like a calculations website that I used to use back then when I was doing mathematics and everything.
Interesting.
It's a really cool website in terms of like if you ever need help with like mathematics and equations and stuff, they do help you out with that.
All kinds of interesting stuff here.
They did upgrade their website, I guess. It's the first time I've been here.
It's not what you look. It's not what you remember saying.
It happens though.
Yeah, for sure. All right, so let's see. Anyways, for those that do end up hopping off at 8, I appreciate you guys, sitting with me and tackling some of these problems. And like I said, I'm going to stay until I get this answer, and then I'll be posting this exact code on GitHub. With once the video is posted, I'll post this code here, and you guys I encourage you to hop on the site and really test out some puzzling puzzles here. Puzzling puzzles, yes.
So I know you guys use Slack for the most part. Do you guys use anything else to like show off like these types of problems that you guys use or go through?
No, I think Slack is the primary way we communicate and to share information. Other than in the CodeStack meetup where we share what we know with the public more openly.
Yeah, I just know that every time I use Slack, it's usually just check up with people that I've already gone through stuff with. But
Mhm.
I like to be kept up with certain notifications. So like even if it's on Facebook or if it's like on a different platform that just notifies me on a what we did the previous night kind of thing,
Right,
it does help.
right. Man, I want to see this number. So here, so these are just notes. So the above is same as below.
Do you mind me asking what the specs on your PC is?
This is a MacBook Pro.
Oh, well, damn.
So it's I mean, like I said, the main problem is that we're doing four loops inside of four loops, and that is like really tough, like to iterate. As I mean, it's like saying compare 100. Say you have 10 people and 10 other people. For everyone to compare each other, you have to compare the first one to the 10, then you go to the second one and compare all 10, and the third one compare all 10, and then fourth one. So you're doing 100 comparisons for those 10 by 10 people, right? Now imagine 600 numbers comparing to 600 numbers. That's a lot of comparisons. It's like 6 million comparisons that for this to try and find the exact number you're looking for. And we're not doing that once, we're doing it twice. So there's a double loop here, there's a double loop here. It's expensive. But like I said, I tried to do this as simple logically, like visually logically as possible without really going into link and more I would say more advanced programming tools. But to make this really come down in time,
As
I
simple
think
logic as possible.
it'd have to use some of those tools to
Yeah,
make it go faster.
I see what you're saying. Like in terms of like what we can do as a simple logic equation, it's not as much as we can do with advanced logic with the other
Right,
tools that are available.
right. I think what I'll even do, is once this is finished and I get the correct answer, I'll add a problem 3. So this will be problem 3, right? So I'll add this problem 1, problem 2. Yeah, I'll add problem 3, how I did it here, and then I'll add problem 3 efficient, right? And this one will run much faster, and the logic will be a little bit more complex, but you can see that the time can be drastically different as far as how long it takes to run. So that'll be cool. So that'll be something for you to look at later on if you want to. I really want to see this finish, man. Torture. I'm really putting a lot of faith in having that and saying that this logic is right, because whatever number comes out, that's what I'm putting in here. And if it's wrong, it's like, oh no. It's like, how do I debug that? There's 600 million numbers.
Might as well try out that one number that you already got. The only number you already got.
The only number I have so far. Yeah, no, I know it's not that one because that number's not prime. Because I made that number by getting 71, so we'll see. I am anxious to see what's going to happen. What I should have done is printed out what are all the factors. I should have printed out what are all the factors and would have been able to make that work. Ugh. Come on. Come on, little computer, you can do it. Any questions? Programming related, non-programming related?
I mean, I was gonna tell you, if you used Wolfram Alpha to type in that number, it would actually give you the prime numbers for those numbers.
Oh, that's cheating.
Right? I'm just saying, if you
I
need to.
I don't need to. My program technically works. It's just slow.
I believe you too. I believe you too. But I'm just saying, if you want with somebody else, then
That's hilarious. No, this has got to finish eventually. All right, so let me see. Since this is running, I don't necessarily need this to be in here. So let's do this. Let's do, where are you? All right, problem 3, slow. Okay. So we still have to do this part. Like this is, I don't think we can avoid this sad part. Just don't think we can avoid that one. But, and so that's those. So getting primes is linear. So that should be relatively quick. I feel like that should be relatively quick. I think the big problem is this 4 and 4 loop. Yeah, I mean, it's a lot of problems here actually. All right, so how do we get primes? All right, I can make this better. Okay, so here I said for Q equals 2. Did I say that? Yes. Okay. Let's see.
so just to explain the logic between your first.
Right now, there's no difference. Right now, this is the
Well,
same.
no, I'm just saying
and right,
using 2.
oh yeah. So this is the same. I use this the same as up here. It's 2L. I just copied it.
Yeah, but why 2? I know that 2 is an iteration of like.
Well,
It's
2 is
not.
because it's the first prime number we care about.
Mm-hmm.
That's why we're using 2. Because Q is we're making our list of primes. So 2 is the first number we actually care about. One we don't
Because
care
pretty
about
much
because
every even number is divided by 2.
yeah. So it's the first prime number we care about. So we're gonna make sure that one's in the list. But how we get this list matters. So instead of doing this, I'm gonna say primes dot any. Let's see. I'm trying to think here. Q divided by X. No, it's not divided. It's 9%. Equals 0. No. That's not what I want. Oh, all right, so I'm saying here of the list in primes, I want all the numbers that Q is equal to this. No, but I just want true or false here. I want to know if this number is prime.
Shouldn't you
this
just
is
use
true or
booleans in
false.
that regard?
Yeah, so this is what, so in any, so in link, and any function means that if this is true for any of the numbers in the list, then it will return true.
Gotcha. Thank you.
So if in this case, if any of these are true, so if I'm going through the list of primes and this returns true, and that means something was divisible by the prime number. So that means it's not a prime. Okay, so if not t, then prime is false. Else. But I don't know what that prime was, so that's what sucks. I don't know what that prime is, so I can't add it to the list. Do I know what the prime is? Well, Q is less than, no, I do know what the prime is. Primes dot add Q, maybe. Okay, so Q factors, if any numbers divisible by something in the list, then Q is not prime, otherwise it is. Okay. I trust that. I don't need this. So this means if it's not true, so if this is true, if true, then it's not prime. So if it's false, it is prime. Okay. Hope that made sense for everybody.
So what I'm kind of getting at is that we're trying to get to that number. Shouldn't we start off from that number and then go back?
Which number are you thinking?
The number that we kind of were trying to get to, which is like the
600 billion?
Yeah.
So right now we're only looking at the factors. So the factors is some array of numbers that we've decided that those numbers go into the big number.
Mm-hmm.
So the biggest number that of those numbers is the 8 billion number that I tossed in here.
Oh yeah, that's right.
So that's the biggest factor that there is. Now this is not prime, it's not a prime factor, but it's the biggest factor. So that's why we're only going to that 8 billion number.
Right. So we're
So
trying to find
here, what we're doing is we're finding all the primes that are below that factor and adding them to the primes list.
Right. Yeah, sorry, I was kind of getting confused with the purpose.
Yeah, sure. Sorry. So we
That
have
makes
our
a lot
list
of
of
sense.
primes. So now let's say we have our list of primes. Now we got to go through our list of primes and see I want the biggest number in the factor count that's also in my primes count. So we'll do how we find largest match. Improved. So we're looking at the factors array, and we're looking at the primes array. So we need the biggest number that's in both. So let's do, let me think. can we do this? Should we do a join? Maybe a join, intersect. How can we intersect? See, I forget. See, I don't know all the answers. Let's go link, intersect. Spell intersect, right? Intersect, wonderful. So to find the intersect, blah, 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 equals comparator. Yep. Duplicate store, intersect store one equals product comparator. Okay. So factors, let's actually do var new list equals factors dot intersect. And we're going to intersect with the primes, and we're going to say what is the comparator. And the comparator should be able to do a function. Let's do that. Sometimes I get my languages mixed up, so it's, let me see. So we have an example comparator here. Product comparator equals, okay. There's another resource here. Link, intersect, extra. Oh, yeah. Okay. That was close, I think. So this is, oh, some people use a join. Interesting. All right, I'll try a join. One more. I can do that. So that'll be, drop that down. I'm trying to think here. I want a clean way of doing this. Intersect by, intersect include, to list, intersect. Sometimes there's decent examples that we can use, intersect. Let's see. Man, I wonder if you can hear my kids. Let's try this. Since they're simple, it might. Let's see. Item is fine. Let's just console write the item. Yeah, I was overthinking. I think here is where you would add a comparator of how do you compare these things. But since they're integers, I don't think we need. So this is still running. I'm going to abort it. Can't do it. So let's clear. And instead of running this, let's run maybe the faster one. Certainly, I hope it's faster. Problem 3, fast. And I will debug this because I actually want to see progress. So let's at least get to here before we start debugging. Yep. I know it's already going to get there. Thank you. That's the easy one. And here we'll be able to see the big list of factors. Okay, exactly how many factors are we dealing with here? And then we'll jump and see how many primes we're dealing with. Again, this is still a big number, so it's kind of a pain.
Honestly, it feels like a math floor and a math ceiling with two different equations would have helped out. Would have cut it into like
all right, so we have 14 factors here, all right? 14 factors. Not that many, all right? So just to give ourselves a little bit of a head start, I'm going to go ahead and jot these down. So we have 71, 839, 1471, 6857, 59569, and then I have to copy paste the rest. Oh, and by the way, I should probably not just wait for this guy to finish. I should go ahead and calculate primes. Oh, I lost them. I shouldn't have done that. Well, I got a head start, at least. You probably hear my kid laughing. Okay, so we should be coming up here. So the next stop will be in this intersect before we actually find. So again, this is still looking for all the primes. I think this is a big factor of why it's slow. Now, if we had actually like a library of primes instead of trying to figure them out every time for every number you do, like this is where databases would be a huge help. You would store information in a database and work from there instead of trying to calculate all these primes over and over again.
Start off your previous save file.
Right. Let's see. Come on. Really hoping. So I think this is the factors part is really the biggest. The primes is really the biggest chore. So that being said, this is a pretty big number. What is this number? -1. So this is using the largest number. Got to make this faster somehow. I don't want to use that number anymore. So what if I use one less? Stop here anymore. I'll stop there, that's fine. So here what I'm doing is instead of using the 8462 billion number, I'm going to use a second number divisible. So that's going to be the 600 billion divided by 839. So that'll be, let me figure out what that is. Clear. Divided by 839. So that'll be the second largest divisible number. So that number is 700 million. So that's significantly less than 8 billion. So hopefully after we get through this little hard part here of getting these numbers, hopefully the primes are slightly more speedy. Okay,
I actually started to see what happened with those iterations. You were going by iteration of 1 or 2.
right.
It's a long number to go by.
Yeah. So we're looking at the first number, and the first number is Q is 2, and if 2, why is Q 2? Oh, we're looking for primes. That's fine. Just want to make sure I'm going to go through the first couple to make sure we're at least getting the numbers correctly. So Q, see that? No one noticed. In a while loop, you have to actually iterate Q. So Q has to be incremented. So that was a big part in why this never really finished, is because we never are incrementing Q. The joys of debugging. Okay, so that being said, it's a big find there. I think that'll make a big improvement for finding our issue. And I appreciate you guys hanging out. That's I don't know if you have other plans, but really want to see this through.
I'm gonna say hello with you. We're in too deep already. We gotta solve this.
We're in too deep. We gotta see this result. All right. Come on, let's get through this list. That's why I wanted to print these out, just so I don't have to do this part anymore. But it's okay. Well, I think this will move a little bit better. So T, add Q, that's good. Increment Q. So now Q is 3. This is false. Add 3, good. So this will be 4. This will be true. So it won't add it. All right, so I think our prime calculating is correct. So let's go ahead and see how long this part takes. I think it'll be significantly faster.
We threw that first quarter of college.
Yeah, right. This was the big mistake. All right, so then we should be getting here at some point. This one shouldn't take as long as the first one, so this will be reasonable. Oh, come on, come on, come on, come on. Light at the end of the tunnel. It's coming. I can feel it. We're getting close.
We got the stairs built.
Yeah, at least we can see what number we're at. We're at 900,000. Okay. So as you can see, like going through this each time is not super fast yet. But I wonder if we go the old, you see here, why this was taking so long, because we weren't incrementing Q. Q was just hanging and we were just sitting there watching it. Reminds me of Ren and Stimpy. And Stimpy, you idiot. Come on, we can do this.
Honestly, I'm just thinking about the two stupid dogs. We were just beating each other with a bat.
Yeah, they're just... Like you look at look at shows like cartoons that you watch as a kid, and you're like, why? It's not that funny. This is just ridiculous. But as a kid, you're just cracking up. I hope I saved. Oh, I think I did save because we were. Let's pause it. Where are we at? We're at 1 billion. And what number are we trying to go to? What's factors?
We're barely at the 1.5 million mark.
I know it's brutal. Oh yeah, you know what? And we're going with primes. Like we're just torturing ourselves. I should do the same thing I did here.
1, 2, skip a few.
Yeah, right. I should. If I do this, that'll at least.
Yeah, that makes a lot of sense.
But I gotta restart it. Damn it! All right.
It's gonna be like exponentially faster.
It'll be twice as fast because now I'm skipping numbers, but it's still slow. But I gotta solve this problem for you guys. And we'll know right when we hit here where we'll stop. Like I said, this part's the first like 30 seconds. It's just the tedious part of getting all these numbers. All right, cool. So that's going there. Now let's see what happens. See if this goes any faster. It's going supposed to go twice as fast. Hopefully it does go twice as fast. We're already at 100K. That's a good start. $200K, getting there.
Problem is, you're running it on a MacBook instead of a tower.
Yeah, it's all right. We'll get there, or I'll get there at least. Come on. What we can do is factors.
Which is mining for Bitcoin over here.
Right. I see what base should be if we're using this much horsepower. Oh, really? That's sad. It's only 14 numbers. Let's see where we're at. We're at Q is 110? 1 million? Okay. And we're trying to get to not that one, 0, 1, 2. We're trying to get to yikes, 716 million. Oh, that's brutal.
I think you're gonna have to leave that computer running all night.
Yeah, that's tough, man. Holy smokes. Okay. I just gotta know which one of these is prime. It almost it's like significantly faster for me to punch in 14 numbers here than it is to try and calculate which one is prime. Like I can literally just punch in all these numbers and see which one it is. Oh, but I don't want to.
It's
It
that
makes me.
trial and error thing. It's that trial and
Yeah,
error.
I know. I don't
You got a
want
couple
to.
answers.
I can't. In my heart of hearts, I cannot do
You playing Kingdom Hearts now?
it. Oh, now suddenly this doesn't want to display.
I mean, it seems like that number did jump twice.
There we go. I'm gonna wager it's probably like one of these three numbers. 1, 2, 3, 4, 1, 6, 9. I almost guarantee it's that one. I wonder if that one's even prime. I'm gonna do a prime check. One through 3, 4, 1, 6, 9. Is it prime? Nope, it's divisible by 839. It's not it. Oh, it's divisible by 839. That's so tragic. How many primes do we have so far? We have 84,000 primes of all the possible primes. Holy smokes. There's a lot of primes.
Yeah, we're going through every single prime.
Oh, how can we do this faster? Not sure. There has to be a faster way.
You can
Then again, I did have a significantly faster computer when I was younger.
Nah, I don't believe you.
Let's see. Let's see. Borrow this. Where are we at? Still doing that stuff. These are huge primes. Man. It's getting a lot of primes. Trying to figure out a way to skip a bunch of numbers. Huh. What number are we at? Q is 1 million. Q is only 1 million. It's barely inching up. Oh, it's tragic. Gotta find a way.
So I kind of cheated. So I kind of looked ahead.
Peter.
I don't know if you want me to give you a hint.
Not yet.
All right.
Let's see. Just looking at these, it looks like that's probably prime. I mean, the first three are usually prime, probably the first four. That might be prime. This doesn't look prime. I'd almost probably say it's one of these two numbers. So if I do what number is this? This is 1,400K. All right, if I stop at that number, I'm pretty sure anything bigger than that's not going to cut it. I just want to get to this prod. I want to see if this is right. This intersect. I haven't used intersect in so long. Let's see. So right now we're getting all the primes that are less than this number. I didn't pick this number for any reason other than it's not over 1 million. Because seems that the 1 million marker seems to be our barrier as far as starting to go slow. So I really want to see what we can do here. I think it takes about a minute for us to get to this through this loop. And then I'll probably need to go 400. See if it's here yet. It's not here yet. All right, now it's going through this stuff. That's good. So let's see how long it takes it to do this. Now this is 400K. This will be significantly faster. Well, it won't take as much time because it's less than 1 million at least. And we're at 300K so far. We're plugging right along. Okay, so we have a bunch of primes that are less than that number. Of these 40,000 primes we have, let's see if any of those are in here. The new list. Where's my new list? Result view. So we have 4 primes. So it looks like this might be the number. So that's the biggest one. So as you can see, we'll finish the program. The biggest number of those primes is 657. Now, mind you, I did take a couple shortcuts. I looked at the list and said I don't want to iterate to 1 million. I'm like, if it's gonna be any number, it'll probably be less than 1 million. If I'm wrong, then this computer just cannot handle that CPU, or I don't have the logical know-how at the moment to make this as optimal as possible. But I want to say 6857 is likely the number. Let's see. Oh, it logged me out. Go back. Go back. Did it log me out? Sign in, yeah. Let's do this again. CS meetup. Dang it. Getting tired. CS meetup. Uh, 98525. Do this. Is this the answer? 6857. It's taking a while. It's probably right. Usually if it's wrong, it just spews right back. Cool. Look at that. Baby steps. Problem 3 solved. All right. Well, that's problem 3. That was painful in the sense that it just took us a really long time to calculate those primes. I think there has to be a better way to calculate primes, or even using a prime library would be tremendously faster, because calculating the primes took longer than just getting the factors themselves. But I appreciate you guys, everyone, coming or joining and sticking around. That'll basically be it for today. Again, I'll be posting this video as soon as it compiles and all that good stuff, probably Monday next week, Monday or Tuesday next week, so you guys can revisit this. And I'll post this code that I have here up tomorrow or probably Monday as well. Again, I appreciate you guys coming and joining in and sitting through this with me.
Thanks a lot, James. Appreciate it, man. And it was a lot of hard work, dude.
Yeah, I mean, it's like I haven't, like I said, like I don't have anything preset for these problems. Like I was like, I'm just gonna do them like anyone else would, and so we ran into a bunch of problems that we just sort of any programmer would run into if they're not thinking about it. And so it's just how you learn. Definitely.
I know this will end up being something that I'll be thinking about probably for the next 2 days if there was a better way to do this.
Right. No, it's true. It's true. Yeah.
I'm going to hate myself for this too.
It'll start haunting you. Like,
in the next episode of Dragon Ball Math.
Yeah. Puzzle Master 5.
All right.
So yeah. So again, thank you guys. We'll call it a day, and take care.
Bye-bye.